Alright, hi everyone. So I'm finishing off the lecture. So we've seen most of this online, so I believe the majority of the class was there for lecture already. So I was unable to record the second half of the lecture because the video was compiling. So what I'm going to do is finish that off and then finish up chapter 10. So where we left off in the video, so if you wanted to even check off the last couple of minutes on the YouTube video that's already up there for the first part of chapter 10, right, we were talking about Le Chatelier's principle. The idea of starting at equilibrium. I apply a stress to the system. In this case, I've added more water. And then a process is going to happen to try and alleviate that stress, which means the water flows from left to right in this figure. And then a new equilibrium is going to be established. Oops, I gotta get out of annotation mode. There we go. Don't know why there's a delay. Come on. Everything's new. Every single day, it seems like there's a new problem with trying to switch between slides. Alright, that seems to be taking care of it. Alright. So, that was a macroscopic example of equilibrium, and then how stresses affect positions in equilibrium. So what we're going to concentrate on is on the microscopic level. So how does a chemical reaction, how does that equilibrium respond to a stress placed on the system? So an example that I have here is just hydrofluoric acid reacting with water or dissolving into water. One of the hydrogens on the water, one of the hydrogens on the hydrogen fluoride, or the hydrofluoric acid, is going to be donated to the water. And that's exactly what I see here. And then I have my leftover F-, my fluoride anion. So, what if I start to stress out this system? So if I just started by putting a certain amount of HF into the water, an equilibrium would be set up. How fast? We don't know. We might have to wait a while, right? We're not saying anything about speed. We're just saying that there's an equilibrium established. But we'll make the reasonable assumption that it is at equilibrium. So what's going to happen if I increase the concentration of hydrogen fluoride, assuming that this reaction is already at equilibrium? So that's going to put stress on the system, and it's going to be relieved by increasing the rate of the forward reaction. So what's going to happen is I've put more HF here, and the reaction is going to be driven forward to try and alleviate that stress. So it's like starting out, if we have reactants and products on a seesaw, it's like starting out in equilibrium, but what I did here is I put too many reactants, because I increased the concentration of HF, threw things out of equilibrium. Which way is the reaction going to go? Well, reactants have to be converted into products so that you can reestablish a new equilibrium. It won't be the same concentrations as our original starting amount, but a new equilibrium will be established. So, I could do another type of stress. Instead of adding HF, what happens if I remove some of the HF? And so again, we can think of this as a seesaw with reactants and products in equilibrium. I've removed now some of the HF. What that's going to do, actually it should be this way. By removing some of the reactants, it's like taking weight off the seesaw. So now the products need to be flowing towards the reactants again, so that a new equilibrium is reestablished. So in this case, the reverse reaction is going to be what alleviates the stress. And so this is how you usually can deal with Le Chatelier type problems, is imagining a seesaw and then asking yourself, how would the seesaw respond, and then how do I get back to equilibrium? And so what I have down here, it's not all the examples we did, but you can start playing with it, with that example of using a seesaw. But there's 4 different combinations that we can look at and then ask, how is it going to shift the direction? Will things move towards products or reactants, right? I would not recommend memorizing this table unless you really, really need to. More think about it physically, and then if you can play with, you can just immediately do a sketch of this equilibrium seesaw, then you're in good shape. But I'll leave that up to you. So, this was kind of alluded to earlier, but water And part of the reason why it's so why it's so important to biology and life is that it can react or act as both an acid, and it can also act as a base, and it's going to be depending upon the circumstances. And so let's dive into that a little bit. So the ionization of water. So it actually, I don't think the book specifically mentions it, but it's called auto-ionization. Auto being self, effectively, so it's self-ionizing, and it's exactly what we're seeing here. I have one molecule of water, just happens to be oriented in a certain direction. I have a second molecule of water, and what I can see, if they collide in this direction like this, there's an H here that could be donated to one of the lone pairs on the oxygen. So we didn't get too deep into that, but if you think about it, we know it takes 2 electrons to make a bond, and so that's exactly what's happening here. So we're snapping this bond here and making a new one with the new oxygen, so the new oxygen of the new water molecule. And so what we watch, if we can follow it along, right, there's my H2O, right? I guess this figure's a little weird, because if we're following the transfer of the hydrogen, but one of them, regardless of how this works out, one of them has received one of the protons, and now the other one is going to be lacking a proton. And so we have our hydronium and our hydroxide. And again, we can go back and do our quick little test to see what are our charges on our reactants, and the charges total to 0, because we have 2 neutral compounds. And then the charges on the right-hand side total to 0 as well, because I have 1 positive and then 1 minus. So, and because of this auto-ionization of water, if we're following that balanced chemical reaction, oops, should not have gone back. Let's go to pure water. Right, it's like taking, I don't know why today's so frustrating. We can take those 2 molecules of water that are reacting. It sets up an equilibrium. We said one of them forms a hydronium ion, the other one forms a hydroxide. So you can only form 1 molecule or even 1 mole of hydronium if 1 mole of hydroxide or molecule, depending on what size scale you're looking at. So basically what I'm saying is they're always created in 1-to-1 pairs. So that means when water ionizes, the concentration of these 2 products have to be identical for pure water, because it's the only thing that's happening is water is reacting with itself. So this was found out experimentally, that the concentration of hydronium is 1 × 10⁻⁷ molar. It doesn't specifically mention it in the book, but it's going to be at a temperature of 25 degrees C, because if you change that temperature, you're going to change the equilibrium a little bit. Because they're always formed in 1-to-1 pairs, that means at 25 degrees Celsius, and water is pure, that means the concentration of hydroxide is also going to be 1.0 × 10⁻⁷. It sounds very small because it is, but you're on the order of magnitude of micromolar. In that case, I think, or maybe it's smaller. I think it's 100 nanomolar. It's small, but there's plenty of reactions that happen in biology close to that level in concentration. So it's not an insanely small amount, is what I'm trying to get across. So what I have on the right-hand side is just a figure. It's saying that if I have a neutral solution, neutral meaning that I have equal amounts of acid and base, that's exactly what I have here. The concentration of both of them are going to be equal, and the concentration is equal to 10⁻⁷ molar. And we'll see why this comes back later, why we're spending so much time on this 10⁻⁷. So, there's ways that I can mess with this equilibrium that water has established. So, if I don't have pure water, maybe I dilute some hydrochloric acid in there, what I can do is increase the concentration of hydronium. Because it'll be like having 2 reactions at once. My pure water reaction is going on here, where I'm forming my hydronium and my hydroxide. But I can also have a secondary reaction essentially happening. So imagine if I were using that hydrochloric acid, and there's trillions of water molecules around, so just because I'm saying some of it's going through this process doesn't mean others aren't going through this process. So if I wrote, because this is a strong acid, I'm going to draw it as unidirectional, But that H can be transferred to the water. I'm left with chloride and then more hydronium. For us, we don't care what the chloride's doing. It's literally just hanging around doing nothing. But what I can see here is there's my water equilibrium, and I've increased the concentration of hydronium. And that's what you're seeing on the graph on the right. And so the concentration of hydronium is going to go above that equilibrium value of 10 to the negative 7th. These two reactions, they're not separate, they're actually linked, because essentially what you've made is now a more complicated seesaw. So hydronium concentration affects, let me try if I can clean this up a little bit without so many circles. There we go. Right. The hydronium concentration, following Le Chatelier's principle, we know if I increase this, right, because I added the acid, some of it's going to push back and form water, and the only way it does that is to consume hydroxide. So these two reactions are linked. And so if hydroxide is consumed, that's why we see that concentration of hydroxide go down while the concentration of hydronium is going up. And so it's a complicated process. That's why not all of that extra hydronium gets converted back into water. It's beyond this course, but some of it does get consumed and go back to form water. But a good amount of it is saying it's still staying as H3O plus, or hydronium. So that should have changed slides, but it didn't. Oh, I guess, that's why. Why it's super delayed today. I think this issues with the internet. Yeah, because I know my roommate right now, he's having a conference call and having issues too, so I apologize if it's like this is more of a sloppy lecture, I feel like, right now. All right, so that's where we were. Here we are, basic solutions. So basic solutions are going to have a very similar, concept of dealing with the basic solution. What do I mean by that? Again, we can say, what if I start with neutral water? It sets up an equilibrium where the concentration of hydronium and hydroxide are going to be 10 to the negative 7th. Then I add something, say, like sodium hydroxide, which starts out as a solid, and then it's going to dissolve into water. And upon doing that, I'll form my sodium cation and more hydroxide. So just like in the last example with HCl, that cation, the last time it was chlorine, now it's sodium, they're just floating around, making sure the charges balance out. But again, we're going to have this link between the two compounds. I made more hydroxide, well, that's going to affect the equilibrium here. Le Chatelier's principle says I'm going to be going back towards my reactants, and that's going to consume some of my hydronium. And so what we see then is that increase in hydroxide and our decrease in hydronium. So take-home message is that for basic solution, the concentration of hydroxide is bigger than that of hydronium. And I know this was on the last slide, but I didn't specifically mention it. For an acidic solution, the concentration of hydronium is greater than the concentration of hydroxide. So all this slide is summarizing all those points up. There's our neutral sample, there's my acidic sample, and there's my basic sample. So what does this bring us to? Why did I spend so much time talking about water, other than, yeah, it's interesting that it reacts with itself and creates some products in equilibrium? Well, it's actually where we derive the pH scale from. So pH, P is actually, it stands for power. So if we have pH, well, actually, let me do this. Make it a little bit more neat. Let me clear everything. So if we're saying that pH is the power of hydrogen, then we'll find in a second, and I can write this, why it's called power. It's because pH is actually an equation. It's the negative log, and that's the function log. So going back to pre-calc, I believe, log rules. We're not going to do too much with them. We're just basically going to use the log function in the calculator, so don't overthink it. It's just saying it's a log concentration of hydronium. So we know what the concentration of hydronium is. I can take the log of it, multiply that number by a minus, and then you'll get the pH. Literally, that minus is in there just so the pH is a positive number. That's the only reason. So let's talk a little bit about the pH scale. So I think most people have heard that phrase before, either if they're talking about the pH of their pool or their fish tank, but what does it actually mean, right? So it's used to indicate the acidity of the solution. And it's going to range typically, not always, from 0 to 14. You can easily make a solution. All you need to think is that what a 1 molar solution of hydrochloric acid is actually a pH of -1. But in general, it falls between 0 and 14. We're going to see in a little bit why. But remember, we're talking about those concentrations at equilibrium of hydronium and hydroxide. Oops. And we said both of those are going to be equal to 10 to the -7th. This is where we're going to get the 14 from. There's going to be a relationship between the two. So 7 plus 7 being 14, 7 minus 7 is 0. So we'll get to that, but it's kind of foreshadowing. Acidic solutions, and this sometimes throws people off, are actually, because it's a measurement of acidity, but they're going to be less than 7. So as things go from 7 down to 0, the acidity isn't going to increase. Anything at 7 is going to be neutral, and then any solution will be considered basic if its values are greater than 7. So if it's 7 and going up to 14 or more, that's going to be basic, and then 7 is neutral. So let's start to see why, right? So a couple of things to point out. pH equals 7. The concentration of hydronium when water is neutral, we can see have our exponent up there. When our pH is less than 7, it means the concentration of hydronium is actually greater than this number. It gets a little weird, but that's because of the negative log part. So as the concentration of hydronium goes up, the pH actually goes down. And we're seeing the same thing here with the basic solution. Hydronium's concentration is lower than 10 to the -7th. That actually means the pH is going up, again, because of that negative log. So all this slide is saying is we have pretty fairly simple instruments to measure pH. The more common one in a lab would be a pH meter, because it gives you a digital readout of the pH. Other common things would be like pH paper, which you usually use for quick experiments or maybe checking the pH of your pool. And then we'll talk about this at the very end of using compounds called indicators. And so depending on the acidity of the solution, certain compounds will actually change color. And so it's a visual cue if something switches from acid to basic. That's all. Yes, there's a huge delay between my iPad and my computer right now, so that's why you keep hearing me pause. That's why. So what I have listed here is just a summary. I would go through it. It's from the book, but basically it's taking household common material and then telling you what their pH is. And an interesting thing about pH, though, is because it is based on, and I'll write that again, pH equals negative log of the concentration of hydronium, right? Log scales, it actually means if we have going from 1 to 2, if this were a log scale, it's actually a 10-fold change. If I go from 1 to 3, is actually 100-fold change. So every time you go by 1 unit of pH, it changes the concentration 10-fold. So that's why something like lemon juice you can drink at 2.2, but if you drank a solution of 1 molar HCl at a concentration of 1 molar, one, you're gonna basically, that's like drinking lemonade, and the other one, you go to the emergency room, and they're only 2 units of pH apart. So it kind of gives you a sense of how big 1 unit of pH is. It's large. It's 10-fold change in concentration. So how do I actually calculate that number? Because I keep writing that equation down, right? I kept saying that pH equals the negative log of the concentration of hydronium. So maybe we can do a quick example on that. I wasn't planning on doing that here. I do have my calculator, so I can just make one right up the spot. Why don't we go back to that example where I said, if we had a 1 molar solution of hydrochloric acid, what is the pH? Actually, no, not as well. Yeah. Well, actually, we can find out what the pH is. Yeah, that's exactly what we need to do. Sorry. So if I take a look at that, I know HCl, it's a strong acid, so it's going to 100% dissociate. Maybe let me do this really explicitly. I will make that aqueous. It's going to be reacting with water. Because it is strong, it's going to go to about 100% completion, or at least 99.999% completion. This H, because it's an acid, will be donated to the water. It forms chloride and then hydronium. So we need to use a little bit of logic here. At the start of the reaction, my concentration of HCl is 1 molar. And then I let it finish, right? So effectively what I'm saying is, at the start, my concentration of hydrochloric acid is 1 molar. That means at the start, my concentration of hydronium, we're going to call it approximately 0, because 1 molar is way, way bigger than 10 to the negative 7th, which is contributing from the pure water. So don't worry about that. We're just going to make a reasonable assumption that 10 to the negative 7th is approximately 0 for this example. The only reason I can make that assumption is because 1 molar is 7 orders of magnitude bigger than 10 to the negative 7th, and that's 10,000 times more concentrated. That's why we're making the assumption. All right, so back to the math. So we're starting with 1 molar, and then we're starting with 0 hydronium. I let it go to completion, so I basically unpause time. That means if it's going to 100% completion, the concentration of HCl is approximately 0, and then everything gets converted into products. So the concentration of hydronium at the end, let me make that explicit, is going to be equal to 1 molar. So it's actually pretty easy to calculate the pH of strong acids. So let's try that out. So we're saying our concentration of hydronium was 1 molar. So all we need to do is grab your calculator, get comfortable with this. All you have to type in is negative, and then somewhere in your calculator you should have the button for log. Some calculators you might have to search a little bit for it, but if you have another function like 10 raising something to the power, it's usually near there, because those actually are the opposite of each other. So I'm going to take the negative log of the number 1. What you should get is a pH of 0, which is exactly what we saw on the last slide when I was talking about the pH scale. There was a little bit of alluding to earlier. There's a relationship actually between the power of hydrogen and then the power of hydroxide. And so just like the power of hydrogen, the power of hydroxide is equal to negative log of the concentration of OH minus. Convenient relationship is that pH plus POH equals 14. So if we had that last example with a 1 molar solution of HCl, right, we said that had a pH of equal to 0. If I wanted to calculate POH of a 1 molar solution of HCl, all I need to do is use the equation pH plus POH equals 14 and substitute in what I know. Well, the pH I know is 0 plus POH equals 14, so therefore POH must be equal to 14. And that's what you're going to find out when you do all these calculations. And this also explains, too, why pH, when the pH goes down, POH goes up, right? Because there's that equilibrium between hydroxide and hydronium. So that's a convenient relationship and a good one to know. And so this is what we're seeing here. This is more just a little bit more explicit. So pH scale and the concentration of hydronium. So I already mentioned that pH is a log scale, and it's log base 10. So every unit is going to be a 10-fold change in concentration of hydronium, and that's what we got here. As the pH decreases, the concentration of hydronium increases, right? I kind of gave you the heads up of why. It's that negative log feature. When you take logs of big numbers, they get small. And so it kind of has that inverse relationship. But it's also an easy way too, because right now we can see all of our numbers here are just 1, and we can start to see that the exponent is related to the pH. And so that's exactly what we're seeing here. When we're going from 2 down to negative 2 down to negative 4, that's a decrease in concentration of hydronium. And that's why we see an increase in pH. And then it would be vice versa, right? As if we went in the other direction, where my concentration goes up, and then I'll also get the exact opposite. So we see that the pH is going down. And so all I have here is the hydronium hydroxide pH comparison take-home message. Again, we're going from pH of 0 to 14. Concentration of hydronium, for us, and at least in this class, it gets more complicated, but we're going to stick it to pretty simple numbers. We notice that all the exponents are actually, if you just took the absolute value of the exponents, equals the pH. And then what we're noticing here, if we have that relationship we had before, where we said that pH plus POH equals 14, right? So we already did the example when the pH is equal to 0, the POH was equal to 14, and again we're seeing that pattern. Take a look at the exponents. So actually the exponents over here are actually the POH. So interesting connections. But take-home message is basically just realizing pH goes from 0 to 14. It's related to concentration. All right, so I need to go. Actually, I can probably get it done in 15 minutes. So you know what I'll do? I'm going to stop here because I have to go online and teach my lab component for 1101 right now. So this is where we ended in our online lecture on Wednesday. So what I'll do is when I'm done with my 1101 student lab, I'm going to record the last 2 sections for chapter 10, and then we'll be done. So let me just pause the record.